We travel tonight across 12 million light-years of empty space to reach a galaxy where new stars are being born at a pace that seems almost impossible. The galaxy hangs in the darkness, tilted edge-on to our view, glowing with the light of millions of young blue stars scattered through its core. This place, known as M82 or the Cigar Galaxy, creates roughly one new star the size of our Sun every few hours, day and night, year after year, following a rhythm of formation far faster than anything happening in our own Milky Way. Standing here in mind, floating among the brilliant young stars and the glowing clouds of gas, we witness what astronomers call a starburst, where star formation happens not at the gentle pace of normal galaxies, but at a rate that consumes gas and creates stars with extraordinary speed. The light surrounding us comes mostly from massive young stars, each one dozens of times heavier than our Sun and burning with fierce blue-white brilliance. These stars formed recently, within the last few million years, and their intense ultraviolet radiation floods the region with energy that makes nearby gas clouds glow in shades of pink and red. The density of stars here exceeds anything found in the Milky Way's spiral arms, with young suns packed close together in clusters, containing thousands of members within just a few light years. The brightest stars pour out so much light that they would blind any observer looking directly at them. Their surfaces heated to temperatures above 30,000 degrees that create the blue color characterizing all young massive stellar populations. You are listening to the Drowsy Astronaut, where we explore the cosmos slowly and thoroughly, taking time to experience places beyond our reach, but within our understanding. Tonight we float through Starburst Galaxies, regions where stars form every few hours instead of every few years, creating cosmic environments unlike anywhere in our local universe. If you are settling in from wherever you happen to be listening, perhaps leave a comment about what draws you to these journeys through space at the end of your day. The like and subscribe options are there as well, if this kind of patient, cosmic exploration brings you some calm during these hard times. Just an invitation to return whenever you need something vast and real and quietly fascinating to think about as sleep approaches. The gas clouds filling the space between the young stars glow with the soft light of ionized hydrogen, creating the pink nebulae visible throughout the starburst region. These clouds consist mostly of hydrogen atoms that have been stripped of their electrons by the intense ultraviolet radiation from nearby massive stars, leaving bare protons that recombine with electrons and emit light in specific wavelengths that appear pink to our eyes. The nebulae extend across hundreds of light years, their shapes twisted and sculpted by stellar winds and the pressure of radiation pushing against the gas. Some regions appear as smooth, glowing sheets, others as filaments and knots, where density variations create structure, all of it bathed in the blue starlight that dominates this environment. The dust, mixed with the gas, absorbs some of the ultraviolet and visible light from the young stars and re-radiates that energy as infrared, making this galaxy one of the brightest infrared sources in the nearby universe. The dust grains, each smaller than the tiniest particle of smoke, number in the billions of trillions scattered through the clouds. Their combined surface area enormous despite their individual tininess. The infrared glow reveals where the densest dust concentrations hide the most active star formation. Regions so thick with obscuring material that visible light cannot escape, but heat radiation passes through freely. The combination of visible blue light from stars, pink light from ionized gas, and infrared from warm dust creates the full picture of this starburst environment, operating across multiple wavelengths simultaneously. Looking outward from the core toward the edges of the star-forming region, the density of young stars gradually decreases as we move away from the central concentration where formation occurs most intensely. The boundary between the bright starburst core and the quieter outer disk appears gradual rather than sharp, with star formation tapering off over a few hundred light years rather than stopping suddenly. The disk of the galaxy extends beyond the starburst region, containing older yellow and red stars that formed long before this current burst began. Their calm, steady light overwhelmed by the brilliance of the blue stars when viewed from a distance. The older population reminds us that this galaxy existed peacefully for billions of years before something triggered the current extraordinary event. The trigger that started this starburst came from outside, from the gravitational influence of a much larger galaxy called M81 that sits about 150,000 light-years away from M82. The two galaxies interact gravitationally, with M81's much greater mass pulling on M82's gas and stars through tidal forces that distort the smaller galaxy's structure. These tidal forces compress gas clouds within M82, increasing their density until gravity overcomes the internal pressure that normally prevents collapse. The compressed clouds fragment and collapse into stars at rates far exceeding what happens in isolated galaxies, creating the burst we observe today and transforming M82 from an ordinary disk galaxy into this brilliant star-forming factory. The energy pouring out of the starburst region creates effects visible from the outside, particularly the superwind that carries hot gas away from the galaxy in streams extending thousands of light years perpendicular to the disk. The wind consists of gas, heated to millions of degrees by the combined effects of stellar winds from massive stars and shockwaves from supernovae exploding when those stars die. The pressure of this hot gas exceeds the gravitational pull trying to hold it in the galaxy, so it escapes, flowing outward and creating the plumes visible in X-ray images and in certain visible light wavelengths. The superwind represents feedback, the way that star formation affects its own environment, eventually removing so much gas that the burst must slow and ultimately stop. Floating here among the young stars and glowing nebulae, we witness a galaxy transformed by the rapid creation of new suns, the process happening all around us in real time. Though the light showing us these events left M82 12 million years ago. Every few hours, somewhere in the region surrounding us, a new star switches on and another point of light joins the brilliant population already burning. The rate feels almost continuous, with formation happening so often that if we could watch the galaxy over days and weeks, we would see new stars appearing constantly, like lights switching on across a dark landscape. The pace dwarfs anything in the Milky Way, where new stars appear only every year or two, making our home galaxy seem almost dormant by comparison. The lifespan of this burst is limited by the finite supply of gas available to form stars and by the feedback processes that heat and expel that gas. Astronomers estimate that M82's starburst began about 200 million years ago and will continue for perhaps another few hundred million years before the gas supply runs too low to sustain the current formation rate. In cosmic terms, this represents a brief period, a flash of intense activity in a galaxy that has existed for billions of years and will continue existing for billions more. The burst will end, the young massive stars will age and die, and M82 will settle back into a quieter state. But for now, during this temporary but spectacular phase, it blazes with the light of millions of newborn suns. The colors visible throughout the region tell stories about temperature and composition, with blue indicating hot young stars, pink showing ionized hydrogen, orange and red revealing cooler gas and dust, and the overall impression creating a tapestry of light that changes depending on which wavelengths we observe. In visible light, the blue stars dominate, their brilliance overwhelming other colors and making the galaxy appear intensely blue when seen from Earth through telescopes. In infrared, the warm dust glows brightest, revealing the structure of molecular clouds and showing where the most obscured star formation occurs, hidden behind veils of dust. In X-rays, the hot gas of the superwind appears, showing the energetic feedback that marks the consequences of such rapid stellar creation. The physical size of the intense starburst region measures roughly 500 light-years in radius, a volume that would fit comfortably within the space between the Sun and many of the nearest stars in our local neighborhood. This relatively compact region contains the materials and processes creating most of M82's new stars, with the extreme density of gas and the triggering from tidal compression combining to make this small volume extraordinarily productive. Outside this core, the galaxy measures about 37,000 light-years across, smaller than the Milky Way's 100,000 light-year diameter, but the starburst core packs enough activity to make the galaxy outshine many larger systems that form stars at gentler paces. The experience of being here, of floating among stars that did not exist a few million years ago, of witnessing formation happening at this accelerated pace, creates a sense of the dynamic nature of galaxies and the temporary events that punctuate their long histories. Galaxies are not static objects frozen in their current states, but evolving systems that experience phases of activity and quiescence, sometimes triggered by interactions with neighbors, sometimes by internal processes, but always changing over the billions of years of their lifetimes. M82 shows us one of these active phases, a starburst that will eventually end, but that represents a crucial period in the galaxy's evolution, transforming its stellar population and its structure in ways that will persist long after the burst fades. And as we prepare to move deeper into understanding what creates these bursts, what sustains them, and what other galaxies experience similar events, we carry the image of M82's core with us. The brilliant blue stars, the glowing pink nebulae, the dense clusters of newborn suns, all of it happening in a region of space where stars appear every few hours rather than every few years, where the rate of creation exceeds the rate of destruction, and where the universe demonstrates one of its most productive processes operating at extraordinary intensity. To understand what makes the starburst in M82 so remarkable, we step back from the brilliant core and observe the galaxy from a distance, watching how frequently new stars appear compared to the gentle pace of formation in our own Milky Way. The comparison creates the most vivid way to grasp what starburst actually means, not through numbers or measurements, but through witnessing the difference directly. We watch M82 for one full day, 24 hours, and during that time, several new stars ignite in the core region, their fusion beginning. Their light joining the combined glow of millions already burning. Then we turn our attention to the Milky Way and watch for the same period, and we see nothing. No new stars appearing, the formation event so infrequent that an entire day passes without a single ignition. The contrast becomes even clearer if we extend the observation to a full week. In M82, dozens of new stars have appeared by week's end, scattered through the central starburst region, each one a new point of blue-white light, contributing to the overall brilliance. The Milky Way, observed for the same week, might show one new star, perhaps two, or possibly none at all, depending on chance and which regions we happen to be watching. The difference in pace transforms star formation from a rare special event into something nearly continuous, from an occasional occurrence into an ongoing process that never really stops. This acceleration defines what astronomers mean when they say a galaxy is experiencing a starburst, a phase where stars appear so frequently that the galaxy blazes with constant new creation. The visual appearance of M82 reflects this rapid pace directly, as the accumulated light from millions of young blue stars, created over just the last few million years, outshines everything else in the galaxy. Young, massive stars burn blue and bright, each one radiating thousands or tens of thousands times more light than our sun, dominating the appearance despite representing a small fraction of the total stellar population by number. The older, redder stars that formed before the starburst began still exist throughout M82, but their gentler light gets overwhelmed by the fierce brilliance of the young population, making the galaxy appear predominantly blue when we look at it from outside. The color serves as a visual signature of youth, telling observers immediately that this galaxy contains many recently formed stars still in their brief energetic phase, spreading across the starburst core. We see hundreds of distinct clusters where stars form together from the same molecular cloud, each cluster containing dozens to thousands of individual stars, all approximately the same age. These clusters appear as bright knots in telescopic images, regions where the stellar density concentrates enough that individual stars blur together into glowing patches. The pink nebulae surrounding many clusters mark regions where the star's ultraviolet light has ionized nearby hydrogen gas, causing it to fluoresce in the characteristic reddish color that creates such beautiful contrast against the blue stellar light. The combination of blue clusters and pink nebulae scattered throughout the core creates a tapestry of formation, each element representing a slightly different moment in the ongoing burst. The dust, mixed throughout the star-forming region, absorbs much of the ultraviolet and visible light from the young stars, heating up and then re-radiating that energy as infrared light, invisible to our eyes but detectable with special instruments. This infrared glow, actually exceeds the visible light output, making M82 one of the brightest infrared sources in the nearby universe, despite appearing as a modest-sized galaxy in visible wavelengths. The dust serves as a mediator between stellar energy and observable light, capturing the fierce radiation from hot stars and converting it to gentler wavelengths that can escape the dense core without being absorbed again. The process creates the peculiar situation where the most active star formation sometimes happens in regions that appear dark in visible light, but blaze brilliantly in infrared. Comparing M82's frantic pace to the Milky Way's leisurely formation reveals not just a difference in speed, but a fundamental difference in how the galaxy operates during this phase. Our galaxy forms stars steadily, distributed across the spiral arms, with new stars appearing here and there as individual molecular clouds become unstable and collapse. The formation happens gently enough that the galaxy maintains a relatively stable appearance and structure over hundreds of millions of years, with gradual changes rather than rapid transformation. The gas supply gets consumed slowly, ensuring fuel for star formation will last billions of years into the future, possibly longer than the remaining lifetime of the universe. M82, by contrast, burns through its available gas at a pace that cannot be sustained indefinitely, trading longevity for intensity, compressing what might take billions of years into a few hundred million at most. The galaxy consumes its molecular clouds rapidly, converting the raw material into stars much faster than our Milky Way does, like a fire burning hot and bright, rather than smoldering slowly. The intense pace means the burst cannot last forever, as eventually the fuel will run out or the feedback from all those young stars will heat and expel the remaining gas, bringing the frantic formation period to an end. The temporary nature makes starbursts special moments in a galaxy's life, brief phases of transformation between longer periods of quieter evolution. The frequency of new stars appearing, roughly one every few hours in M82, compared to one every year or two in the Milky Way, translates to vastly different environments for any hypothetical observers. Someone watching the sky from a planet near M82's core would see new stars igniting regularly, the stellar population changing noticeably over timescales of thousands or millions of years, rather than the billions required in normal galaxies. The night sky would appear crowded with brilliant blue stars, far denser than the stellar field visible from Earth, creating illumination levels much higher than the starlight we experience. The environment would feel dynamic rather than static, with stars forming, living briefly, and exploding as supernovae frequently enough that these dramatic events would be almost routine rather than rare cosmic catastrophes. The concentrated region where most formation occurs, spanning just a few hundred light years in radius, packs extraordinary energy output into a relatively small volume. This concentration creates conditions unlike anything in our local galactic neighborhood, where star formation spreads across thousands of light years of spiral arm territory, diffusing the activity across vast distances. The density of young stars in M82's core exceeds typical regions of the Milky Way by factors of 10 or more, creating neighborhoods where stars cluster far more tightly than in the Sun's vicinity. The crowding affects stellar evolution and planetary systems in ways we can only theorize about, as the intense radiation and frequent supernovae would make the environment challenging for the kinds of stable conditions that allowed life to develop on Earth. The light from M82 that reaches us tonight left the galaxy 12 million years ago, carrying information about the starburst as it appeared in that distant past. The formation we observe might have continued unchanged for those 12 million years, or it might have intensified or begun to decline, with any changes invisible to us until their light completes the journey across space. The delay reminds us that astronomical observation always looks backward in time, seeing distant objects as they were rather than as they are, creating a separation between observation and reality that grows with distance. M82's starburst continues right now in the galaxy's present moment, new stars forming, but that present remains hidden from us behind 12 million years of light travel time. The energy pouring out of M82 equals the output of billions of sun-like stars, all that power generated by the combined nuclear fusion of millions of young massive stars and reprocessed by dust and gas into the multi-wavelength glow we observe. The total exceeds what our entire larger Milky Way produces, demonstrating how dramatically star formation rate affects galactic brightness and how bursts allow smaller galaxies to outshine their larger but quieter cousins. The energy flows outward in all directions, some escaping into intergalactic space, where it travels indefinitely until encountering something that absorbs it. Some absorbed locally by dust and gas that re-emit it at different wavelengths, and some driving the powerful stellar winds and supernovae that create the feedback, eventually limiting the burst. Standing once more in the core region, surrounded by the blue stars and pink nebulae, we feel the difference between this environment and the quieter star-forming regions of normal galaxies. The pace of creation here runs faster than elsewhere, new lights appearing constantly, the stellar population growing and changing on timescales short compared to cosmic standards. The burst will not last forever, its intensity ensuring eventual decline, as gas depletes and feedback accumulates. But while it continues, it represents one of the universe's most energetic and beautiful phenomena. The comparison to normal galaxies throws the extraordinary nature of starbursts into sharp relief, making clear that M82 exists in a special temporary state, a phase of transformation that fundamentally shapes the galaxy's future. The experience of witnessing this pace, of seeing the formation unfold at rates impossible in our own galaxy, creates understanding more vivid than any calculation or measurement could provide. We grasp what starburst means through observation rather than definition, through watching new stars appear every few hours, rather than through reciting formation rates and timescales. The knowledge settles into place naturally, built from accumulated experience of light and time and frequency. From comparing the frantic to the calm, and recognizing the difference not as numbers, but as fundamentally different ways for galaxies to create their stellar populations. And having understood the pace and what it means for M82's appearance and evolution, we can now explore the galaxy itself in greater detail, learning what triggered this burst, what sustains it, and what will eventually bring it to an end, all while maintaining the experiential approach that makes these distant processes feel real and present rather than abstract and theoretical. M82 hangs in space as the archetypal example of a starburst galaxy. Studied intensively because it sits relatively close to Earth, and because it displays the starburst phenomenon with exceptional clarity. The galaxy measures about 37,000 light-years across, making it roughly one-third the diameter of the Milky Way, though its compact size belies its impressive luminosity and activity level. The distance of 12 million light-years places M82 in the nearby universe, astronomically speaking, close enough that modern telescopes can resolve individual star clusters and study the structure of the starburst region in detail, impossible for more distant galaxies. The location in the constellation Ursa Major means that observers in Earth's northern hemisphere can see the galaxy year-round, making it a favorite target for both amateur astronomers with backyard telescopes and professionals operating major observatories. The appearance of M82 depends dramatically on viewing angle and wavelength, with the galaxy showing different faces to observers looking in different parts of the electromagnetic spectrum. In visible light, M82 appears as an elongated cigar-shaped object tilted edge-on to our line of sight, showing its disk as a thin line with bright knots of star formation along its length and the distinctive dark dust lanes cutting across the bright regions. The edge-on orientation allows us to see the vertical structure of the galaxy in a way impossible for face-on systems, revealing how the starburst affects the disk's thickness and how super winds blow material perpendicular to the plane. The dust lanes appear as dark ribbons where molecular clouds block the light from stars behind them, creating the mottled appearance that gives the galaxy visual interest and shows the three-dimensional structure. The superwind streaming from M82's core represents one of the galaxy's most distinctive features. Visible as plumes of hot, glowing gas, extending thousands of light-years above and below the disk plane. These outflows consist of gas heated to millions of degrees by energy from young, massive stars and from supernovae, with the combined pressure of stellar winds and supernova shocks, driving the material outward faster than the galaxy's gravity can hold it. The superwind becomes visible in X-ray images showing the hot gas, in optical images showing specific emission lines from ionized elements, and in radio observations tracing the magnetic fields that thread through the outflowing material. The plumes extend perpendicular to the disk because that direction offers the path of least resistance, with less gas to push through compared to the dense disk plane where resistance would slow the outflow. The structure of the superwind reveals the power of stellar feedback operating in this system, with the combined energy output from millions of young stars creating a fountain of gas that redistributes material throughout the galaxy's halo and beyond into intergalactic space. The gas carries heavy elements produced in stars and dispersed by supernovae, enriching the halo and potentially seeding the intergalactic medium with metals that might later participate in forming new galaxies or stars. The outflow also removes gas from the disk that might otherwise have formed additional stars, creating a self-regulating mechanism where intense star formation produces effects that limit continued formation. The balance between gas consumption through star formation and gas removal through outflows determines how long the burst can continue before the supply drops too low to sustain high rates. The cause of M82's starburst lies in its gravitational interaction with M81, a large spiral galaxy sitting about 150,000 light-years away and appearing close to M82 in Earth's sky. though at slightly greater distance from us. M81 contains roughly 10 times M82's mass, making it the gravitationally dominant member of this small group of galaxies. And its tidal forces pull on M82 every time the two galaxies pass near each other during their orbital dance. The most recent close approach occurred roughly 200 million years ago, triggering the current burst through tidal compression of M82's molecular clouds. The galaxies will continue interacting for billions of years, possibly eventually merging into a single larger system, though their current relative velocities suggest they might instead remain gravitationally bound companions for the foreseeable future. The tidal interaction works by creating forces that vary across M82's extent, pulling harder on the near side than the far side, and thereby stretching the galaxy along the line toward M81, while compressing it perpendicular to that line. These tidal forces disturb the orbits of gas clouds within M82, causing some clouds to collide with others and creating shockwaves that compress gas to higher densities. When density exceeds the threshold for gravitational collapse, star formation begins, initially in scattered regions, but eventually spreading throughout the disturbed zone as feedback from newly formed stars triggers formation in neighboring clouds. The process created the central starburst region we observe, concentrated within roughly 500 light-years of M82's center, where the tidal compression was strongest and where the molecular gas concentration was highest before the interaction began. The stellar population within M82's starburst region shows the characteristic signature of recent formation, dominated by hot blue stars that have ages of only a few million years, and that will burn through their nuclear fuel in just tens of millions of years before exploding as supernovae. These massive stars, with masses ranging from 10 to 50 or more times the Sun's mass, provide most of the visible light, despite representing only a small fraction of the total number of stars formed. As most newly formed stars are small red dwarfs that contribute little light, the massive star population creates the intense ultraviolet radiation field that ionizes surrounding hydrogen, the powerful stellar winds that push against nearby gas, and eventually the supernovae that will feed energy into the superwind and heat the surrounding medium. The infrared brightness of M82 rivals or exceeds its visible brightness, making the galaxy one of the brightest infrared sources in the nearby universe and earning it classification as a luminous infrared galaxy, though not quite reaching the ultraluminous category reserved for the most extreme cases. The infrared emission comes from dust grains heated by absorbing ultraviolet and visible light from young stars, with the dust reaching temperatures of a few tens of degrees Kelvin in cooler regions to a few hundred degrees in the warmest zones nearest to massive star clusters. The total infrared luminosity implies that roughly half of the starburst's energy output gets absorbed by dust and re-radiated at longer wavelengths, demonstrating the importance of dust in regulating the energy balance and in making many starburst regions optically thick to visible light, though transparent to infrared. The X-ray emission from M82's superwind reveals gas heated to millions of degrees, temperatures so extreme that atoms are stripped of most or all of their electrons, and the resulting plasma radiates characteristic X-ray photons. The X-ray luminosity traces the mechanical energy input from stellar winds and supernovae, showing how much power the starburst injects into its surroundings and how that energy thermally heats the outflowing gas. The spatial extent of the X-ray emission, reaching thousands of light years from the disk, demonstrates that the feedback affects volumes much larger than the star-forming region itself, with consequences extending throughout the galaxy's halo. The temperature and density structure of the X-ray emitting gas provides information about the age of the outflow and the rate of energy injection, allowing astronomers to model the burst's history and predict its future evolution. The history of M82's starburst extends back roughly 200 million years based on the ages of stellar populations and the modeling of the galaxy's interaction with M81, though the exact timeline remains somewhat uncertain. The burst likely began gradually as the tidal interaction first compressed gas clouds, intensified as more clouds collapsed and feedback began spreading formation to neighboring regions, and now may be approaching peak intensity, or perhaps beginning the slow decline toward lower rates as gas consumption and outflows reduce the available supply. The current rate of 10 solar masses per year represents a snapshot of an evolving system that was forming stars more slowly in the past and will form them more slowly again in the future as the burst winds down over the next few 100 million years. The designation Messier 82 reflects the galaxy's inclusion in Charles Messier's famous catalogue of nebulous objects, compiled in the late 18th century, with Messier observing the galaxy in 1774 and recording it as a faint fuzzy patch without resolving any detail. For nearly 2 centuries, M82 remained just another catalogued nebula, interesting but not particularly notable, until modern telescopes and spectroscopy revealed its extraordinary star formation rate and unusual features. The transformation from catalogue entry to intensively studied starburst prototype demonstrates how astronomical understanding deepens over time as observations improve and as theoretical frameworks develop too. Explain what observations reveal. M82 now serves as the comparison standard against which other starbursts are measured, the galaxy whose properties define what a moderate starburst looks like, and whose detailed study informs our understanding of the broader phenomenon. And as we move from M82 toward other examples of galaxies experiencing rapid star formation, we carry the image of this tilted disk with its brilliant blue core, its dark dust lanes, its superwind plumes, all created by tidal forces, compressing gas and triggering formation at rates 5 to 10 times faster than normal, transforming a modest spiral galaxy into one of the showcase examples of starburst activity in the nearby universe. The antennae galaxies appear in Earth's sky as a pair of colliding spiral galaxies, locked in gravitational embrace, their long tidal tails of stars and gas extending outward like the antennae of an insect and giving the system its common name. The two galaxies, formerly designated NGC 4038 and NGC 4039, began their collision roughly 600 million years ago, when they first passed close enough for gravitational forces to distort their structures and trigger bursts of star formation. The ongoing merger represents a more extreme version of the interaction affecting M82, with the two antennae galaxies actually interpenetrating rather than merely passing near each other, creating multiple sites of intense star formation distributed throughout the colliding system. The distance of about 45 million light-years places the antennae farther than M82, but still well within the nearby universe, close enough for detailed study with modern telescopes. The appearance of the antennae changes dramatically depending on whether we observe the overall system or zoom in to examine specific star-forming regions distributed through the merger. From a distance, the system shows two bright nuclei where the original galactic cores still exist as separate structures, long curved tidal tails streaming outward in opposite directions, where tidal forces pulled stars and gas from the galaxy's outer regions, and a complex chaotic central zone where the two disks overlap and interact. The tidal tails extend more than 300,000 light-years from the merger center, dwarfing the original galaxies and creating structures visible even in modest amateur telescopes. The tails contain billions of stars pulled from their original orbits by the tidal forces of the collision. Stars now following paths taking them far from the merger site, though many will eventually fall back toward the combined system over hundreds of millions of years. Zooming into the central merger region reveals dozens of bright knots that high-resolution imaging resolves into compact star-forming regions called superstar clusters. Dense aggregations of young stars that may represent the most intense star formation sites in the nearby universe. Each superstar cluster contains thousands to millions of stars packed into regions just a few light-years across, creating stellar densities thousands of times higher than in normal open clusters in the Milky Way. The clusters appear brilliant blue from the combined light of their massive young stellar members, with some clusters so luminous that they outshine entire dwarf galaxies despite their compact size. The formation of these superclusters resulted from the collision compressing molecular clouds to extraordinarily high densities, allowing gravity to create these dense stellar aggregations rather than the more dispersed clusters that form in quieter environments. The total star formation rate across the entire antennae system reaches roughly 10 to 20 solar masses per year, comparable to or slightly exceeding M82's rate, but distributed across a much larger volume encompassing both original galaxies and the overlap region. The distribution means that the antennae show multiple starburst sites rather than a single concentrated region, with star formation happening in the overlap zone, where gas clouds from both galaxies collide. Along the spiral arms that still partially exist in the outer disks, and even in some regions of the tidal tails where compressed gas achieved sufficient density to collapse. The spread of star-forming regions creates a more extended starburst compared to M82's concentrated core, demonstrating the variety of configurations that starburst galaxies can display, depending on the specific geometry and history of their triggering interactions. The merger timeline extends across roughly 1 billion years total, from first approach through final coalescence, with the current state representing a middle phase where the galaxies have passed through each other once and are now falling back for a second passage that will more completely combine their structures. The first passage, 600 million years ago, created the initial burst of formation, with subsequent evolution and the ongoing return pass sustaining elevated formation rates through repeated compression events as the galaxies gravitationally settle into a single system. The cores will eventually merge completely, perhaps a few 100 million years from now, creating a single massive nucleus surrounded by a disturbed halo of stars pulled from both progenitor disks. The final product will likely resemble an elliptical galaxy, with the ordered spiral structure of the original galaxies erased by the violent merger process and replaced by a more spheroidal distribution of stars. The colors visible in high-resolution images of the antennae tell the story of star formation and stellar populations through a palette ranging from blue to pink to yellow to orange. The brilliant blue knots mark sites of recent formation, where young massive stars dominate the light, while pink regions show ionized hydrogen gas glowing from ultraviolet radiation from those same young stars. Yellow and orange tones reveal older stellar populations formed before the merger or during earlier phases of the collision. Stars that have aged since their formation and cooled to produce redder light than the hot blue giants. Dark dust lanes cut across many of the star-forming regions, showing where molecular clouds block the light from background stars and indicating the locations of dense gas that may form the next generation of stars. The Hubble Space Telescope images of the antennae rank among the most spectacular astronomical pictures ever captured, revealing individual star clusters and nebulae scattered throughout the merger and showing the delicate structures created by the collision with exquisite clarity. The images resolved what ground-based telescopes could only hint at, transforming the antennae from a fuzzy, peculiar object into a detailed landscape of star formation and galactic interaction. The pictures show the violent beauty of galaxy mergers, illustrating how destruction and creation proceed simultaneously as the collision rips apart the original structures while triggering extraordinary rates of new star formation. The visual impact makes the antennae one of the most recognizable and frequently reproduced images in popular astronomy, introducing countless people to the phenomenon of starburst galaxies. The young stars, formed in the antennae's superstar clusters, will themselves influence the merger's future evolution through the same feedback processes operating in M82, with stellar winds and supernovae heating and potentially expelling gas that might otherwise form additional stars. The clusters are so dense that stars occasionally collide or interact gravitationally, creating exotic outcomes impossible in the sparse stellar fields of normal galaxies. Some clusters may evaporate over time as their stars disperse, while others might survive as globular clusters orbiting the eventual merger remnant, serving as fossils of this merger event visible billions of years from now, when the starburst itself has long since ended. The comparison between M82 and the antennae illustrates two different paths to starburst activity, with M82 triggered by a gravitational interaction between galaxies that remain separate, while the antennae result from an actual collision that will culminate in complete merger. Both mechanisms compress gas and trigger enhanced star formation, but the different geometries create different distributions of star-forming regions and potentially different total amounts of stars formed over the lifetime of the burst. The gravitational interaction affecting M82 may produce several bursts over billions of years as the galaxies repeatedly pass near each other, while the antennae's merger will produce one extended burst culminating in the coalescence and then likely little subsequent formation as the merged system settles into a gas poor elliptical configuration. The antennae also demonstrate that mergers can create structure even as they destroy the original spiral forms, with the tidal tails representing new, large-scale features formed purely through gravitational dynamics during the collision. These tails may eventually fall back toward the merger center, but they will not reform into spiral arms, instead merging into the spheroidal halo that characterizes elliptical galaxies. The temporary nature of the tails reminds us that many structures we observe in the universe exist only briefly in cosmic terms, created by transient interactions and gradually erased by subsequent evolution. The antennae's tails will look very different a billion years from now, and many of the brilliant star-forming regions will have faded as their young stars age and the gas supply diminishes. And as we move from these specific examples toward understanding the mechanisms that create all starbursts, we carry images of both the concentrated nuclear burst in M82 and the distributed superstar clusters throughout the antennae. Two variations on the theme of interaction triggered rapid star formation, both showing how gravitational forces between galaxies can compress gas and create the conditions for stars to form at extraordinary rates. The mechanisms that trigger starburst events all involve compressing molecular gas to densities high enough that gravity can overcome the internal pressure that normally prevents clouds from collapsing, creating conditions where star formation proceeds rapidly rather than at the gentle pace characterizing isolated galaxies. The compression can result from several different processes, but galaxy interactions and collisions represent the most common triggers, responsible for the majority of starburst galaxies observed in the nearby universe. When two galaxies pass near each other, their gravitational fields create tidal forces that pull and squeeze gas in both systems, disturbing the equilibrium that previously prevented collapse and initiating the chain of events leading to a burst. The strength of the tidal forces depends on the masses of the interacting galaxies and on how close they approach, with closer encounters and more massive companions producing stronger compression and potentially more intense resulting starbursts. The tidal forces work because gravity decreases with distance, meaning the near side of a galaxy experiences stronger pull toward a companion than the far side, creating a stretching force along the line connecting the two systems, and a compression force perpendicular to that line. This pattern of forces distorts the gas distribution in both galaxies, driving gas towards certain regions while pulling it away from others, and creating the conditions for enhanced star formation in the compressed zones. The distortion also drives gas inward toward galactic centers in many cases, funneling material from outer regions where density is too low for efficient formation toward nuclear regions where higher densities make collapse easier. The inflow of gas to central regions partially explains why many starburst galaxies show concentrated nuclear starbursts like M82 rather than formation distributed throughout their disks. The actual collapse of molecular clouds occurs when the density reaches a threshold value where the cloud's self-gravity exceeds the thermal pressure, magnetic pressure, and turbulent motions that provide support against collapse. In normal galaxies, molecular clouds hover near this threshold, with some regions occasionally exceeding it and forming stars, while most regions remain stable. The compression from tidal forces or collisions pushes many clouds simultaneously over the threshold, creating synchronized collapse across large volumes and producing the elevated formation rates that define a starburst. The compression need not be enormous to trigger the effect, as clouds already near the threshold require only modest additional squeezing to tip them into collapse, making even relatively gentle interactions capable of triggering bursts if conditions align properly. The triggering often creates a chain reaction where the first generation of stars formed after compression begins to affect their surroundings through winds and supernovae. And these feedback effects can trigger formation in neighboring clouds through compressive shocks that propagate through the interstellar medium. The shock waves from supernovae represent particularly effective triggers, creating shells of compressed gas that sweep through surrounding material and collect gas into dense layers where formation can occur. This propagating, or sequential star formation, means that the burst can spread beyond the initially compressed regions, potentially affecting larger volumes than the triggering interaction directly disturbed. The chain reaction continues until feedback becomes so strong that it heats and disperses gas rather than compressing it, shifting from formation triggering to formation suppressing as the burst evolves. Major galaxy mergers, like the one creating the antennae, represent the most extreme triggering mechanism, producing the highest star formation rates through violent compression as gas-rich disks interpenetrate and collide. During a merger, gas clouds from the two galaxies can collide directly at relative velocities reaching hundreds of kilometers per second, creating strong shocks that compress the gas and trigger immediate collapse. The multiple passages that occur during merger, as the galaxies fall through each other, swing around, and fall through again, create repeated compression events that can sustain high formation rates for hundreds of millions of years. The eventual coalescence of the cores funnels enormous amounts of gas into the nuclear region of the merger remnant, potentially creating an extremely intense nuclear starburst that may be accompanied by growth of a central supermassive black hole, as gas falls not just into star-forming clouds, but also into the very center of the gravitational potential. Minor mergers, where a small galaxy falls into a larger one, can also trigger bursts, though typically less intense than major mergers, with the size difference affecting the strength of compression and the total amount of gas disturbed. A dwarf galaxy merging with a spiral might trigger a nuclear starburst in the spiral, as the dwarf's infall drives gas inward. But the total formation rate may remain modest compared to major mergers between similarly sized systems. The frequency of minor mergers exceeds major mergers in most galaxy populations, making them potentially important contributors to the overall starburst population, despite their individually lower intensities. Many galaxies likely experience multiple minor mergers over their lifetimes, each one triggering a modest burst that enhances formation for a few 100 million years before fading. Internal mechanisms can also trigger bursts without requiring galaxy interactions, though these typically produce less intense starbursts than merger-driven events. Galactic bars, elongated structures of stars and gas extending across the centers of many spiral galaxies, can drive gas inward through gravitational torques that remove angular momentum from gas orbiting in the disk. The inflow concentrates gas in nuclear regions where increased density triggers enhanced formation, creating nuclear starbursts similar to those seen in interacting systems, but without requiring an external companion. Bar-driven bursts tend to be less intense than interaction-driven events, but they can sustain moderate formation rate enhancements for extended periods as the bar continues funneling gas inward. The prevalence of bars in spiral galaxies suggests that this mechanism may affect a significant fraction of galaxies at some point in their evolution. Environmental effects in galaxy clusters represent another triggering mechanism, particularly relevant for cluster galaxies, where interactions with the hot intracluster gas or with other cluster members can compress galactic gas and trigger formation. Ram pressure stripping, where a galaxy moving through the cluster's hot atmosphere experiences pressure from the gas it's plowing through, can compress the galaxy's own gas and trigger bursts in regions where the compression is strongest. Close encounters with other cluster galaxies can produce tidal compression, similar to interactions in the field, though the high velocities typical of cluster galaxies often mean brief encounters rather than the prolonged interactions possible when galaxies move more slowly relative to each other. The complex cluster environment creates multiple potential triggering mechanisms operating simultaneously, making cluster starbursts potentially different in character from field examples. The timescales over which these triggering mechanisms operate range from the relatively sudden compression during collision, which can begin forming stars within millions of years of the encounter, to the more gradual processes, like bar-driven inflows that build up over tens or hundreds of millions of years before accumulating enough gas centrally to trigger a burst. The different time scales create different burst characteristics, with rapid triggers potentially producing more intense peaks that decline quickly as feedback and gas consumption reduce the formation rate, while gradual triggers may produce longer-lasting but less intense bursts that extend over substantial fractions of a galactic orbit. The observation that different starbursts show different intensities and durations likely reflects this variety in triggering mechanisms and in the detailed conditions within each galaxy when triggering occurs. Understanding triggers helps explain why starbursts occur where and when they do, why some galaxies experience bursts while others do not, and how the population of starburst galaxies evolves over cosmic time as merger rates and interaction frequencies change. The gravitational nature of most triggers means that starbursts occurred more frequently in the early universe when galaxies were closer together and interactions more common, helping explain the observed increase in cosmic star formation rate at earlier times. The eventual future decline in mergers as cosmic expansion separates galaxy groups implies that starbursts will become rarer in the distant future, making them characteristic of certain cosmic epochs rather than eternal features of the universe. And as we move from understanding what triggers bursts to examining the material those triggers compress, we carry the knowledge that galaxy interactions, collisions, bars, and environmental effects all can compress molecular gas beyond the threshold for collapse. That the compression initiates bursts that can spread through chain reactions, and that different triggers produce different intensities and durations of resulting star formation. The molecular clouds that serve as the raw material for star formation in starburst galaxies represent the densest concentrations of gas in the interstellar medium, regions where hydrogen molecules rather than individual atoms dominate, and where temperatures drop low enough for gravitational collapse to overcome thermal pressure. These clouds consist primarily of molecular hydrogen, the two-atom molecule written as H2 in chemical notation, though this dominant component, ironically, remains largely invisible to direct observation because the simple symmetric structure produces weak emission at the cold temperatures characterizing cloud interiors. The clouds reveal themselves instead through emission from trace molecules like carbon monoxide that form in the same regions and that emit efficiently in radio wavelengths, allowing astronomers to map the molecular gas distribution throughout galaxies and measure the total mass available for forming stars. The typical molecular cloud in a normal spiral galaxy contains thousands to millions of solar masses of gas, distributed across regions ranging from a few to hundreds of light years in extent, with internal densities reaching hundreds to thousands of molecules per cubic centimeter in the densest cores. These densities vastly exceed the sparse distribution of atoms in most of the interstellar medium, where typical values measure only 1 atom per cubic centimeter or less, but they remain incredibly tenuous by terrestrial standards, creating vacuums far better than anything achievable in laboratory conditions on Earth. The temperature within the clouds drops to 10 to 50 Kelvin, cold enough that most gas exists in molecular rather than atomic form, and cold enough that thermal motions provide minimal support against gravitational collapse. The combination of high density and low temperature creates the conditions necessary for star formation, though additional compression often needed to push clouds over the threshold where collapse actually begins. In starburst galaxies, the molecular clouds show differences from their counterparts in normal systems, typically displaying higher densities, larger masses, and closer spatial concentrations that collectively contribute to the enhanced formation rates. The compression from tidal forces or collisions creates clouds that exceed the threshold for collapse more easily, while also creating more numerous clouds as gas compression fragments larger volumes into discrete, collapsing units. The result is more clouds forming stars simultaneously, with each cloud potentially forming stars at similar rates to clouds in normal galaxies, but the larger number of active clouds producing the elevated total formation rate that defines the starburst. Some starburst clouds also show higher efficiency in converting their gas into stars, possibly because the higher densities or stronger compression overcomes turbulence and magnetic fields that can slow formation in gentler environments. The molecular gas observations use the emission from carbon monoxide molecules, which emit photons at specific radio wavelengths when they transition between rotational energy states, with the intensity of emission depending on how much carbon monoxide exists along the line of sight through the cloud. Astronomers calibrate the relationship between carbon monoxide emission and total hydrogen mass through observations and theoretical calculations, allowing them to estimate the total molecular gas content of galaxies from carbon monoxide maps. The technique works reliably in most environments, though complications arise in the hottest starburst regions, where intense radiation from young stars can destroy carbon monoxide molecules or heat them to temperatures where the normal relationship between emission and mass breaks down. Advanced observations using multiple molecular tracers help overcome these complications and provide accurate gas mass estimates, even in extreme starburst environments. The spatial distribution of molecular gas determines where star formation can occur, with regions lacking dense molecular clouds showing little or no formation, regardless of other conditions. In M82, the molecular gas concentrates toward the nucleus, creating the central starburst region where formation occurs most intensely, while the outer disk contains less gas and shows correspondingly lower formation activity. The antennae display molecular gas concentrated in the overlap region, where the two galaxies interpenetrate, in knots along the remnant spiral arms, and in a few locations in the tidal tails, where compression has collected sufficient material to create clouds. The gas distribution directly determines the distribution of young stars, creating the visible structure of the starburst when observed in wavelengths that trace recent formation. The process by which molecular clouds fragment into smaller cores that ultimately collapse into individual stars or small stellar groups involves turbulence, magnetic fields, and gravity operating simultaneously across a range of scales, from the cloud as a whole down to the cores measuring fractions of a light year across. The turbulence creates density fluctuations within the cloud, with some regions becoming denser than average and others more diffuse. And the densest regions can fragment further if they exceed the local threshold for gravitational instability. The fragmentation continues hierarchically, with larger structures breaking into smaller ones, until the fragments become small and dense enough that they collapse into protostars and eventually ignite fusion to become main sequence stars. The efficiency of this fragmentation process and the final distribution of stellar masses depend on details of turbulence, heating, cooling, and magnetic field properties that remain active areas of research. The timescale for molecular clouds to collapse and form stars extends from roughly 1 to 10 million years from initial compression to the appearance of young stars, a timescale short compared to galactic evolution, but long enough that the triggering events and the visible starburst they produce separate by millions of years. The delay means that observations of starbursts reveal conditions from a few million years ago, rather than the immediate present, though in most cases, the burst evolution proceeds slowly enough that current observations represent the same phase as existed a few million years earlier. The short formation timescale compared to stellar lifetimes also means that star formation represents a nearly instantaneous process from the perspective of galactic evolution, with cloud collapse and stellar ignition happening essentially immediately, compared to the billions of years those stars will exist afterward. The depletion of molecular gas through star formation and through expulsion by feedback determines how long a starburst can continue and how much of the original gas supply ultimately converts into stars. Measurements of molecular gas content in starburst galaxies, combined with star formation rate estimates, allow calculation of depletion times, the time required to consume all the gas at current formation rates, typically yielding values of a few hundred million to a few billion years. These depletion times set upper limits on burst durations, though in practice most bursts end sooner as feedback and gas consumption combine to reduce the available supply below levels that can sustain high formation rates. The fraction of gas that ultimately becomes stars, called the star formation efficiency, typically ranges from a few percent to perhaps 30%, depending on how strong feedback becomes and how much gas gets expelled versus consumed. The molecular gas also serves as a reservoir of heavy elements accumulated over the galaxy's previous star formation history, with atoms of carbon, oxygen, nitrogen, and other elements beyond hydrogen and helium mixed into the gas from earlier generations of stars that died and dispersed their fusion products. The presence of these metals affects cloud properties, including opacity to radiation, cooling rates, and the chemistry that creates complex molecules, potentially influencing how clouds collapse and what stellar masses result from the collapse. Starburst galaxies in the early universe formed from gas with much lower metal content than present-day systems, possibly creating differences in stellar populations and formation efficiencies that make distant starbursts somewhat different from the nearby examples we can study in detail. The dust mixed with the molecular gas, though tiny in total mass compared to the gas, profoundly affects observations and the thermal state of star-forming regions through its opacity to visible and ultraviolet light, and its emission in the infrared. Each dust grain consists of solid material, typically silicates or carbon compounds, with sizes ranging from nanometers to micrometers, and the combined cross-section of countless grains creates enough obscuration to block visible light completely in the densest cloud cores. The dust absorbs radiation from young stars and re-radiates that energy at longer wavelengths, shifting the starburst's energy output from visible and ultraviolet into the infrared, and making many starbursts brightest in wavelengths invisible to human eyes. The dust also provides surfaces where certain molecules can form more easily than in gas phase reactions, contributing to the molecular chemistry that creates the complex species detectable in cloud observations. And as we move from understanding the clouds themselves to examining how the stars formed from those clouds, affect their environment, and ultimately limit further formation, we carry the knowledge that molecular clouds provide the essential raw material, that their properties determine where formation can occur, and that their depletion through formation and expulsion sets the duration of any burst. The young massive stars formed during a starburst immediately begin affecting their surroundings through powerful stellar winds, intense ultraviolet radiation, and eventually through supernova explosions when they exhaust their nuclear fuel and die, creating feedback processes that couple the energy output from star formation back into the galactic gas, and ultimately regulate or quench the burst. The feedback starts as soon as the most massive stars ignite fusion and begin producing ultraviolet photons energetic enough to ionize hydrogen atoms in surrounding gas, stripping electrons from the atoms and creating regions of ionized hydrogen that appear pink in visible light from the characteristic emission wavelength when electrons recombine with protons. These HII regions, as astronomers designate ionized hydrogen zones, expand around young massive stars as the ionization front pushes outward into neutral gas, creating bubbles that can grow to tens or hundreds of light years in diameter around the most luminous stellar groups. The stellar winds from massive stars represent steady streams of charged particles flowing outward from stellar surfaces at speeds reaching thousands of kilometers per second, driven by radiation pressure and carrying away small fractions of the star's mass, but substantial amounts of momentum and energy. An individual massive star can drive winds with mass loss rates around 1/1,000,000th of a solar mass per year. Modest compared to the star's total mass, but significant when multiplied by the thousands or millions of massive stars in a starburst region, and integrated over millions of years of stellar lifetimes. The winds collide with surrounding gas and create shockwaves where the fast-moving wind material plows into slower-moving interstellar gas, heating both to millions of degrees and creating hot bubbles of X-ray emitting plasma. The pressure in these bubbles exceeds the pressure in surrounding cooler gas, causing the bubbles to expand and push the cooler material away from the stellar sources. The combination of many stellar winds operating simultaneously in a starburst region creates a collective effect far more powerful than individual winds could achieve, with the hot bubbles merging and combining their energy to create a super bubble that can blow out of the galaxy's disk entirely if the combined pressure exceeds the gravitational pull holding gas in the galaxy. This blowout creates the super winds visible in galaxies like M82, where hot gas streams perpendicular to the disk and carries material thousands of light years from the star-forming region. The superwind represents a major pathway for energy and momentum from star formation to couple into the larger galactic environment, transporting not just energy, but also chemically enriched material from stellar fusion and carrying that material into the halo and potentially beyond into intergalactic space. The ionizing radiation from massive stars affects more than just the immediate surroundings, as the ultraviolet photons can travel large distances before being absorbed, creating extended ionized regions and heating gas across substantial volumes around starburst regions. The heating raises gas temperatures from the few tens of Kelvin typical of molecular clouds to 10,000 Kelvin or higher in ionized zones, increasing thermal pressure and making the gas more resistant to gravitational compression. The ionization and heating can prevent nearby molecular clouds from collapsing, effectively slowing star formation in regions surrounding areas that already contain young massive stars. This effect contributes to the self-regulation of star formation, where the process of forming stars creates conditions that inhibit further formation, providing negative feedback that can stabilize formation rates or drive them downward as feedback strengthens. The supernova explosions that mark the deaths of massive stars represent the most violent feedback process, releasing energies equivalent to roughly 10 to the 51 power ergs in a few seconds as the stellar core collapses and the outer layers explode outward at velocities reaching 10,000 kilometers per second or more. Each supernova injects as much energy into the interstellar medium as millions of years of stellar wind output, creating a powerful shockwave that sweeps up surrounding gas and compresses it, while also heating it to extreme temperatures. The shock can trigger star formation in dense clouds it encounters, compressing them over the threshold for collapse, but it also destroys clouds through heating and dispersal, with the net effect depending on local conditions, including gas density and cloud structure. In dense starburst environments, supernova shocks overlap and create a hot component of gas that fills substantial volumes and contributes to the superwind, along with material from stellar winds. The time delay between the formation of massive stars and their supernova deaths means that supernova feedback begins only after the first few million years of a burst, with the most massive stars exploding first, followed by progressively less massive stars over tens of millions of years. This delayed onset means that early phases of bursts experience primarily wind and radiation feedback, with supernovae becoming important contributors only as the burst matures and the first stellar generation begins dying. The accumulation of supernova energy over time can ultimately create enough heating and pressure to expel substantial gas masses from the galaxy, or at minimum, to heat that gas enough to prevent further collapse, contributing to the eventual decline and quenching of the burst. The supernova rate in intense starbursts can reach several per year, far exceeding the roughly 1 per century rate in the Milky Way, making supernova feedback much more significant in starbursts than in normal galaxies. The heavy elements produced through fusion in massive stars and dispersed by supernovae represent another feedback effect, enriching the interstellar medium with metals that affect the properties of subsequent star formation by increasing cooling rates, changing dust content, and altering molecular chemistry. The enrichment builds over time as successive generations of stars form from gas containing the products of previous generations, progressively increasing the metallicity of the gas and the stars formed from it. In starbursts, this enrichment proceeds rapidly due to the accelerated formation rate and the high proportion of massive stars that die quickly and return processed material to the gas. The metal content affects cloud opacity, making metal-rich clouds more opaque to radiation and potentially allowing them to cool more efficiently. Though the details of how metallicity affects formation efficiency remain areas of active research. The removal of gas from star-forming regions through expulsion in superwinds represents perhaps the most important feedback effect for regulating bursts, as gas removed from the galaxy obviously cannot form additional stars, and gas heated to millions of degrees cools too slowly to collapse on timescales shorter than the burst duration. The mass loading of superwinds, the ratio of outflowing gas mass to star formation rate, determines how efficiently feedback removes gas, with higher mass loading meaning more gas expelled per star formed, and therefore stronger regulation of the burst. Observations suggest mass loading values ranging from 1 to 10 or more in various starbursts, meaning that for every solar mass of stars formed, 1 to 10 solar masses of gas get expelled in the superwind. Removing gas faster than formation consumes it, and guaranteeing that bursts cannot continue indefinitely, even if other processes did not intervene. The spatial structure of feedback effects creates zones around star-forming regions where conditions differ dramatically from both the cold, dense molecular clouds and the hot, ionized bubbles, with warm, neutral, or partially ionized gas occupying substantial volumes and creating complex multi-phase structures that determine how energy and momentum couple into the interstellar medium. The complexity means that simplified models treating gas as a single temperature component may miss important effects, requiring sophisticated simulations that follow gas at a range of temperatures and densities to capture the full feedback physics. The observations providing constraints for such models come from multi-wavelength observations showing different gas phases, from cool molecular gas traced in radiocarbon monoxide emission, through warm ionized gas visible in optical emission lines, to hot X-ray emitting plasma, heated by shocks and stellar winds. The self-limiting nature of star formation through feedback creates a mechanism that can in principle stabilize formation rates, rather than allowing them to run away to extreme values, as increased formation produces more feedback, which reduces formation back toward lower rates. This negative feedback loop operates on timescales of millions to tens of millions of years, roughly the time required for massive stars to form, live, and explode. creating regulation that prevents formation from consuming all available gas instantly while allowing bursts to continue for tens to hundreds of millions of years before ultimately quenching. The balance between triggering processes that compress gas and promote formation, and feedback processes that heat and expel gas and inhibit formation, determines the character and duration of any particular starburst, with different balances producing the variety of intensities and durations observed among real starburst galaxies. And as we move from understanding how feedback regulates bursts to examining the full life cycle of starbursts from ignition through peak to decline and quenching, we carry the knowledge that stellar winds, radiation, and supernovae all couple energy into galactic gas, that this feedback heats, ionizes, and expels gas, and that the cumulative effect ultimately limits burst durations and determines how much gas converts to stars versus being removed from the galaxy. The life cycle of a starburst begins with a quiescent phase before the triggering event, when the galaxy forms stars at normal rates, determined by its gas content and internal dynamics without external disturbances enhancing formation. This pre-burst phase can last billions of years, with the galaxy aging gradually as it slowly converts gas into stars, evolves chemically as dying stars return enriched material to the interstellar medium, and maintains the structure characteristic of its morphological type, whether spiral, irregular, or elliptical. The molecular gas exists in clouds that occasionally collapse to form stars, but most clouds remain gravitationally stable, hovering near but not exceeding the threshold for collapse, creating the low, steady formation rates typical of normal galaxies. The stellar population accumulated during this phase consists of stars at all ages from the galaxy's formation to the present, creating a mixed population dominated by older, lower-mass stars, with some younger stars scattered through recent formation sites. The trigger initiates the burst through processes already discussed, compressing molecular gas and pushing many clouds simultaneously over the threshold for gravitational collapse, beginning the transformation from normal to starburst galaxy. The onset occurs gradually rather than instantly, with formation rates increasing over millions of years as compressed clouds collapse and as feedback from the first generation of newly formed stars begins triggering formation in neighboring clouds through propagating compression. The initial increase may be modest, perhaps doubling or tripling the formation rate before the triggering mechanism fully develops its effects, creating an early phase where the galaxy transitions from normal to starburst without yet showing the extreme rates that characterize peak activity. This onset phase can extend from 10 to 50 million years, depending on the nature of the trigger and the distribution of molecular gas, with faster compression from violent collisions producing quicker onset than gentler tidal interactions. The peak phase represents the period of maximum star formation rate, occurring when compressed gas is abundant, feedback has not yet expelled or heated substantial amounts of material, and the triggering compression has fully developed its effects. Peak formation rates depend on the amount of gas compressed and the intensity of compression, ranging from a few solar masses per year in modest bursts to hundreds or thousands per year in the most extreme ultraluminous infrared galaxies experiencing major mergers. The peak can last tens to hundreds of millions of years if gas supplies remain adequate, and if feedback does not quench formation too quickly, during which time the galaxy produces the bulk of the stars that will form during the entire burst. The appearance of the galaxy changes dramatically during this phase, shifting from whatever colors characterized the pre-burst state to intensely blue from the combined light of millions of young massive stars, with infrared luminosity also peaking as dust absorbs and re-radiates the prodigious energy output. The decline phase begins when gas depletion and feedback combine to reduce the available supply of molecular gas below levels that can sustain peak formation rates, causing rates to drop gradually back toward more modest values. The decline typically proceeds more slowly than the rise, extending over hundreds of millions of years as the remaining gas forms stars at decreasing rates and, as feedback continues, expelling or heating gas. The formation does not stop suddenly, but rather fades gradually as fewer and fewer clouds exceed the threshold for collapse, and as feedback makes the remaining gas increasingly resistant to collapse through heating and turbulence injection. The stellar population formed during the peak begins aging during this phase, with the most massive stars dying as supernovae and leaving behind neutron stars or black holes, while the less massive stars continue shining, gradually shifting the population's color from blue to somewhat bluer than the pre-burst average. The quenching marks the end of significant starburst activity, occurring when the formation rate drops back to levels comparable to or below the pre-burst rate, effectively ending the burst and returning the galaxy to a quiescent or normally star-forming state. Quenching can result from complete gas exhaustion, where essentially all molecular gas has either formed stars or been expelled, leaving insufficient material for continued formation, or from feedback-driven heating that raises gas temperatures enough to prevent collapse, even though substantial gas masses remain. The quenched galaxy enters a post-starburst phase, characterized by aging stellar populations formed during the burst, with the youngest stars determining the galaxy's appearance and properties during the early post-burst period. The massive blue stars die quickly, within tens of millions of years of quenching, causing the galaxy's blue light to fade and its color to redden as intermediate mass stars become the dominant young population. The post-starburst phase can extend billions of years, with the stellar population formed during the burst aging and evolving while little new formation replenishes the young stellar component. The galaxy's color continues reddening over this period as successive mass ranges of stars exhaust their nuclear fuel and leave the main sequence, with the timescale for different masses determining the color evolution rate. A galaxy quenched after a major burst might show a prominently blue color for a few 100 million years as massive stars still exist, transition to intermediate colors as those massive stars die but intermediate mass stars remain, and eventually settle to red colors dominated by low-mass stars after 1 billion years or more. The spectral features visible during this phase provide fossil evidence of the earlier burst, showing absorption lines characteristic of particular stellar types and abundances of heavy elements enhanced by the burst's chemical enrichment. The possibility of repeat bursts exists for galaxies that retain or reaccumulate molecular gas after quenching, with new interactions or internal processes potentially triggering subsequent episodes of enhanced formation. Some galaxies may experience multiple bursts over their lifetimes, each separated by quiescent periods, creating complex stellar populations, recording several distinct formation episodes. The repeat bursts may occur at regular intervals if the triggering mechanism operates periodically, such as in galaxy pairs orbiting each other and interacting every few 100 million years, or irregularly depending on random encounter rates with other galaxies. The identification of previous bursts in currently quiescent galaxies relies on stellar archaeology, analyzing stellar populations to identify age components corresponding to earlier formation episodes. The final outcome of the burst depends on its intensity and on the mass of the galaxy, with massive systems potentially surviving bursts without dramatic morphological transformation, while lower mass galaxies may have their structures significantly altered by feedback and gas removal. Major mergers driving the most intense bursts often transform disk galaxies into ellipticals through the violent process of collision and coalescence, erasing spiral structure and creating the spheroidal distributions characteristic of elliptical systems. The merger remnants settle into dynamically relaxed configurations over hundreds of millions of years after the actual collision concludes, with stellar orbits becoming randomized through gravitational relaxation, and the final structure determined by the total mass and angular momentum of the merging systems. These remnant ellipticals typically show little ongoing star formation and red colors from aged stellar populations, representing the ultimate evolutionary state reached after a merger-driven burst and subsequent quenching. The timescale from trigger to quenching spans typically a few 100 million to perhaps 1 billion years, shorter for intense bursts that rapidly consume gas and produce strong feedback, longer for gentler bursts where moderate formation rates allow extended durations before depletion or quenching occurs. The total mass of stars formed during this time can range from millions to hundreds of billions of solar masses, depending on the initial gas supply and the burst intensity, representing a substantial fraction of the galaxy's final stellar mass if the burst was intense, or a modest addition if the burst was relatively weak. The burst leaves permanent marks on the galaxy, including the stellar population created, the chemical enrichment from supernova products, potentially morphological transformation if the burst involved a major merger, and possible removal of enough gas to prevent subsequent significant star formation. The cosmic significance of bursts lies partly in their ability to rapidly transform galaxies, creating in a few 100 million years changes that might otherwise require billions of years of steady evolution. The bursts serve as drivers of galaxy evolution, particularly in the early universe, when interactions were more common and when many galaxies likely experienced one or more bursts during their histories. The observation that many present-day elliptical galaxies show spectral evidence of post-starburst aging, and that many likely formed through major mergers, suggests that bursts played important roles in creating the galaxy population we see today. Understanding burst life cycles, therefore, contributes to understanding galaxy evolution broadly, connecting present-day galaxies to their earlier states and to the processes that shaped them over cosmic time. And as we move from this theoretical understanding of burst evolution to the historical discovery and observational characterization that revealed these phenomena to human knowledge, we carry the framework of a life cycle beginning in quiescence, triggered into activity, peaking, declining, and quenching, with various pathways and timescales producing the diversity of bursts observed throughout the universe. The recognition that some galaxies form stars far more rapidly than normal emerged gradually through the 20th century, as observations revealed unusual galaxies with properties difficult to explain, through standard models of steady galaxy evolution. The earliest cataloguing of nearby galaxies, including Charles Messier's famous catalogue, compiled in the 1770s, identified objects like M82 as fuzzy nebulae without understanding their extragalactic nature or recognizing any unusual star formation. As the telescopes and photographic techniques of that era could not resolve structure or measure properties indicating rapid formation, the nature of nebulae remained debated well into the 20th century, with the question of whether they were objects within the Milky Way or separate galaxies beyond it not definitively settled until Edwin Hubble's observations in the 1920s demonstrated that some nebulae contained Cepheid variable stars, whose distances placed them far outside our galaxy. The development of radio astronomy in the 1940s and 50s revealed that some galaxies emit strongly in radio wavelengths, showing emission far exceeding what normal stellar populations would produce, indicating some energetic process beyond ordinary star formation. The radio sources, in some cases, correlated with optically peculiar galaxies showing disturbed morphologies or unusual colors, suggesting connections between radio emission and galactic interactions, or nuclear activity. The distinction between radio emission from star formation, from active galactic nuclei powered by supermassive black holes, and from other sources required decades to clarify through improving observations and theoretical understanding. Some radio galaxies turned out to host active nuclei, while others showed emission from widespread star formation, with the radio spectra and morphologies helping distinguish the different source types. The infrared revolution arrived with the launch of the Infrared Astronomical Satellite, abbreviated IRAS, in 1983, a space telescope that surveyed the entire sky in infrared wavelengths and discovered populations of galaxies radiating enormous amounts of energy in the infrared, but appearing relatively faint and visible. Light. These infrared bright galaxies, many showing evidence of ongoing mergers or interactions, revealed star formation hidden behind thick dust that absorbed visible and ultraviolet light and re-radiated that energy at infrared wavelengths invisible to ground-based optical telescopes. The IRAS mission transformed understanding of the starburst phenomenon by showing that many of the most active star-forming systems had been invisible or unecrogaced in optical surveys, their true power only becoming apparent when observed in wavelengths that penetrate dust. The mission's all-sky survey provided the first comprehensive census of infrared luminous galaxies and established infrared luminosity as a key diagnostic of star formation rate. The Hubble Space Telescope's launch in 1990 and its subsequent imaging of nearby galaxies revealed starburst regions in exquisite detail, showing individual star clusters and nebulae and demonstrating the complex structures created by rapid star formation and feedback. The Hubble images of M82 revealed the superwind structure more clearly than ground-based observations ever could, while pictures of the antennae resolved the superstar clusters and showed the intricate morphology of the merger. The ability to observe in ultraviolet wavelengths from above Earth's atmosphere added crucial data on hot young stars and their ultraviolet emission, complementing infrared observations of dust-obscured formation and providing more complete census of total formation activity. The Hubble observations transformed abstract starburst galaxies into detailed landscapes that could be explored visually and compared to theoretical predictions. The development of spectroscopy, the technique of separating light into its component wavelengths and measuring emission and absorption at specific colors, provided tools for measuring star formation rates, gas compositions, and stellar populations quantitatively, rather than relying on images alone. The detection of emission lines from ionized hydrogen, oxygen, and other elements allowed measurement of gas properties, including temperature, density, and ionization state. While the strength of these emissions directly correlates with the ultraviolet radiation field from young stars, providing star formation rate estimates. Absorption lines in galaxy spectra reveal stellar populations and their ages, allowing detection of post-starburst galaxies through spectral signatures characteristic of intermediate-age stellar populations. The combination of imaging and spectroscopy created comprehensive characterization of starburst galaxies, including their formation rates, stellar populations, gas contents, and chemical compositions. Radio observations using millimeter and submillimeter wavelengths, developed from the 1980s onward, provided techniques for mapping molecular gas through carbon monoxide emission, revealing the fuel for star formation and showing where formation might occur before stars actually form. The correlation between molecular gas content and star formation rate provided empirical laws describing how efficiently gas converts to stars under different conditions, with starburst galaxies generally showing higher efficiency than normal disk galaxies. The completion of the Atacama Large Millimeter Array, abbreviated ALMA, in Chile during the 2010s revolutionized molecular gas observations through unprecedented sensitivity and resolution, allowing detailed mapping of molecular clouds within starburst galaxies and revealing structures down to scales of light years within systems millions of light years distant. X-ray observations from satellites like Chandra revealed hot gas in superwinds and allowed measurement of supernova rates through detection of individual supernova remnants and diffuse emission from hot plasma heated by accumulated supernova shocks. The X-ray observations confirmed theoretical predictions that stellar feedback heats gas to millions of degrees and drives outflows, providing direct evidence for the feedback processes limiting burst durations. The combination of X-ray data showing hot gas, optical data showing ionized regions, infrared showing dust, radio showing molecular clouds, and ultraviolet showing young stars created multi-wavelength portraits of starburst galaxies showing all components of the star-forming ecosystem operating simultaneously. The discovery in the late 1990s and early 2000s of extremely distant starburst galaxies at high redshift, seen as they appeared billions of years ago when the universe was younger, revealed that starbursts occurred frequently in the early universe and contributed substantially to building the stellar populations of galaxies during cosmic epochs when formation rates exceeded present-day values. These distant starbursts often appear as submillimeter galaxies, sources detected in long-wavelength observations that pierce through dust to reveal intensely star-forming systems at large distances. The population of high redshift starbursts demonstrated that the phenomenon occurred throughout cosmic history, and that understanding local starbursts provides insight into processes that operated when the universe was younger and more active. The theoretical framework for understanding starbursts developed alongside observational discoveries, with simulations of galaxy collisions showing how interactions trigger compression and enhanced formation, models of stellar feedback predicting superwind properties, and calculations of burst evolution connecting triggering mechanisms to observable properties. The theory and observations informed each other, with simulations making predictions that observations tested and observations revealing phenomena that required theoretical explanation. The convergence of increasingly sophisticated observations and improving theoretical models created the current understanding of starbursts as temporary phases of enhanced formation triggered primarily by interactions regulated by feedback and ending through gas depletion or heating, with the details varying among systems, but the broad framework applying universally. The human element in these discoveries deserves recognition, with generations of astronomers contributing observations, developing instruments, analyzing data, building theories, and passing knowledge to successors who continued the work. The field progressed through collaboration and competition, with different groups pursuing similar questions through different approaches and comparing results to build consensus. The major discoveries often came unexpectedly as new instruments revealed unanticipated phenomena, requiring flexibility to recognize when observations contradicted expectations and when new frameworks were needed to explain surprising results. The story of starburst research exemplifies how science advances through patient accumulation of evidence, development of new observational techniques, and iterative refinement of theoretical understanding over decades. And as we move from this historical account to surveying the diversity of starburst galaxies discovered through these efforts, we carry appreciation for the decades of work that transformed starbursts from unrecognized phenomena to well-characterized events with understood physical mechanisms, observable properties, and recognized importance for galaxy evolution. The diversity of starburst galaxies reveals itself through a tour of examples beyond M82 and the antennae, each system showing variations on the common theme of enhanced star formation, while displaying unique characteristics that reflect different triggering mechanisms, host galaxy properties, or evolutionary states. The galaxy NGC 253, also called the Sculptor Galaxy, appears as a nearly edge-on spiral, similar in orientation to M82, but located in the southern sky and showing a more extended starburst distributed along its spiral arms in addition to a concentrated nuclear component. The galaxy sits roughly 11 million light-years away, making it one of the nearest starburst systems and allowing detailed study of individual star-forming regions throughout its disk. The formation rate reaches several solar masses per year, modest compared to M82, but still exceeding what the galaxy's size and mass would predict for normal star formation, qualifying it as a starburst. Though not an extreme example, the Southern Pinwheel Galaxy, designated M83, shows a different configuration, with the starburst occurring primarily in the spiral arms, rather than concentrated in the nucleus, creating a distributed pattern of formation regions, visible as knots of pink emission along the arms. This galaxy appears nearly face-on from Earth, allowing excellent views of its spiral structure and the locations of active formation, with Hubble images resolving hundreds of individual star-forming regions and superstar clusters scattered throughout the disk. The total formation rate reaches roughly 1 to 2 solar masses per year, borderline between normal and starburst, but included in starburst studies due to the presence of superstar clusters, with properties similar to those in more extreme systems. The face-on orientation and relatively close distance of 15 million light-years make M83 valuable for studying the detailed structure of star-forming regions in an environment moderately enhanced over normal disk galaxy formation. The dwarf starburst galaxy, NGC 1569, demonstrates that intense star formation can occur even in small systems containing far less mass than giant spirals like the Milky Way. This irregular dwarf sits roughly 11 million light-years away and contains only a small fraction of a large galaxy's stars. Yet, it forms stars at rates approaching 1 solar mass per year, extraordinarily high relative to its low total mass. The burst in NGC 1569 has created superstar clusters visible even from millions of light-years away, with some clusters containing hundreds of thousands of stars packed into regions a few light-years across. The trigger for this dwarf's burst may have been inflow of gas from the intergalactic medium or an interaction with another dwarf, though the exact mechanism remains uncertain, demonstrating that starbursts can occur in diverse environments and through various processes. The Tadpole Galaxy, designated UGC 10214, shows an extreme tidal tail extending nearly 300,000 light-years from the main galaxy body, created when a compact intruder galaxy passed through the disk and pulled out a stream of stars and gas through tidal forces. The head of the tadpole contains multiple starburst regions triggered by the compression from the interaction, while the tail shows some star formation in knots, where gas collected into dense enough concentrations to collapse. The disturbed morphology and the visible intruder galaxy still embedded in the disk make the tadpole an excellent laboratory for studying how interactions trigger bursts and how tidal features form during such events. The distance of 420 million light-years places the tadpole well beyond the nearby universe, but still accessible to detailed study with large telescopes. The giant elliptical galaxy Centaurus A, one of the nearest large ellipticals at roughly 13 million light-years, shows evidence of a relatively recent merger that triggered starburst activity in its inner regions, despite the host galaxy's elliptical morphology that normally indicates an evolved system with little ongoing formation. The galaxy displays a prominent dust lane cutting across its face. When viewed edge-on, material likely accreted from a smaller companion that merged with the elliptical and brought fresh gas to fuel new formation. The formation rate in the inner few thousand light-years reaches modest values insufficient to classify Centaurus A as a strong starburst. But the presence of young stars in an elliptical galaxy demonstrates that even evolved systems can experience bursts if they acquire gas through mergers or accretion. The galaxy also hosts an active nucleus powered by a supermassive black hole, showing how starbursts and active galactic nuclei can coexist when mergers deliver gas to both star-forming regions and to the central black hole. The ultraluminous infrared galaxy ARP 220 represents the extreme end of the starburst spectrum, a major merger between two gas-rich galaxies that has triggered star formation at rates exceeding 200 solar masses per year, hidden behind such thick dust that the system appears relatively faint in visible light while blazing in infrared. The two galactic nuclei remain separated by about 1,000 light-years. Not yet merged, but surrounded by dense concentrations of molecular gas and dust, where formation proceeds at extraordinary rates. The total infrared luminosity exceeds 1 trillion suns, making ARP 221 of the most luminous galaxies in the nearby universe and a prototype ultraluminous infrared galaxy. The dust obscuration is so extreme that even infrared wavelengths cannot penetrate to the very center, requiring radio observations to map the molecular gas distribution and reveal the structure hidden at shorter wavelengths. The galaxy NGC 6240 shows a merger in progress, similar to the antennae, but at a more advanced stage, with the two nuclei separated by only a few thousand light-years and surrounded by disturbed streams of stars and gas created by the interaction. High-resolution observations reveal that both nuclei contain supermassive black holes that will eventually merge into a single, more massive hole when the galaxies complete their coalescence. The starburst activity occurs throughout the system with particular concentration near the nuclei, driven by gas inflows created by the tidal forces of the merger. The complexity of the system, with multiple star-forming regions, two active nuclei, extensive tidal features, and hot gas from superwinds, demonstrates the rich phenomenology created when gas-rich galaxies undergo major mergers. The common threads connecting these diverse examples include enhanced star formation rates above normal levels, triggering by interactions or mergers in most cases, though internal processes trigger some examples, and temporary nature with bursts representing phases rather than permanent states. The diversity appears in the range of formation rates, from barely enhanced to ultraluminous, in the distribution of formation from concentrated nuclear bursts to distributed spiral arm activity, in host galaxy types, from dwarf irregulars to giant ellipticals, and in evolutionary states, from recently triggered to declining post-peak systems. The variety demonstrates that the starburst phenomenon encompasses a spectrum of intensity and character rather than a single well-defined category, with galaxies transitioning smoothly from normal formation through moderate bursts to extreme ultraluminous states. The study of this diverse population allows identification of patterns and relationships connecting observable properties like infrared luminosity or molecular gas content to formation rates and burst characteristics, creating empirical frameworks for understanding how bursts work. The comparisons reveal which properties correlate with formation intensity, how gas consumption rates scale with burst strength, and how feedback properties vary among systems with different rates. The recognition that diversity exists prevents overgeneralization from single examples, like M82, ensuring that theoretical frameworks accommodate the full range of observed behaviors rather than just explaining the most studied cases. The future discovery of additional starburst galaxies, particularly at high redshift, where the most intense bursts occur, but where observational challenges make detection and characterization difficult. We'll continue expanding the known diversity and testing whether current frameworks adequately describe all manifestations of the phenomenon. The James Webb Space Telescope's infrared capabilities will reveal previously hidden populations of dust-obscured starbursts in the distant universe, while improving radio facilities will map molecular gas in ever more distant systems. Each new discovery adds to the census and potentially reveals configurations or properties not represented in the current sample, pushing understanding forward through confrontation with new data. And as we move from this gallery of diverse examples to contemplating what the study of starburst galaxies teaches us about galaxy evolution and cosmic star formation, we carry the knowledge that bursts occur in many types of hosts, span a wide range of intensities, result from various triggers, and share common characteristics despite their diversity. The scientific importance of studying starburst galaxies extends beyond understanding these systems themselves to informing broader questions about galaxy evolution, star formation physics, and the history of stellar mass buildup across cosmic time. The insights gained from detailed study of nearby starbursts, where individual regions and structures can be resolved, and where multi-wavelength observations provide comprehensive characterization, apply to understanding more distant galaxies in earlier cosmic epochs, where direct, detailed study remains impossible with current technology. The local starbursts serve as laboratories where star formation operates at intensities similar to high redshift galaxies, but close enough for thorough investigation, creating templates and physical understanding applicable to interpreting distant systems visible only as faint smudges even in the most powerful telescopes. The role of galaxy mergers in driving the most intense starbursts provides crucial information about how galaxies grow and evolve through hierarchical assembly, where small systems merge to form larger ones over cosmic history. The major mergers that trigger ultra-luminous starbursts represent key transformative events in galaxy evolution, rapidly building stellar mass while consuming or expelling gas, and potentially transforming disk galaxies into ellipticals. The observation that many present-day elliptical galaxies show spectral evidence consistent with past starburst phases, and that merger remnants often resemble ellipticals, suggests that merger-driven starbursts played important roles in creating the elliptical galaxy population. Understanding the merger starburst elliptical connection helps explain the observed galaxy morphology distribution and the bimodality of galaxy properties into star-forming spirals and quiescent ellipticals. The physics of star formation under extreme conditions, revealed through starburst studies, tests whether the relationships between gas properties and formation rates measured in the Milky Way apply universally, or require modification in different environments. The star formation law connecting gas density to formation rate shows that starburst galaxies generally form stars more efficiently than normal disks, converting higher fractions of their molecular gas into stars per unit time. Understanding what creates this efficiency difference, whether higher densities, stronger compression, different turbulence properties, or other factors, refines theoretical models of star formation and improves predictions of how galaxies form stars across different environments and cosmic epochs. The empirical relationships derived from nearby starbursts provide calibrations for calculating formation rates in distant galaxies where only indirect traces are measurable. The feedback mechanisms operating in starbursts, particularly the coupling of energy and momentum from young stars into the galactic gas through winds and supernovae, represent key processes in galaxy evolution that determine how efficiently galaxies convert gas into stars and how much gas gets ejected into intergalactic space. The super winds visible in systems like M82 demonstrate that feedback can expel gas at rates comparable to or exceeding formation rates, removing material that might otherwise form stars and enriching the circumgalactic medium and intergalactic medium with heavy elements. The metal enrichment of intergalactic gas, observed through absorption line studies, may partly result from winds driven by starbursts throughout cosmic history, making starbursts important contributors to chemical evolution beyond their host galaxies. Understanding feedback quantitatively allows prediction of galaxy evolution, including when gas will be depleted, how much will be expelled, and what stellar masses galaxies will ultimately achieve. The contribution of starbursts to the cosmic star formation rate density. The total rate of star formation per unit volume of space, averaged over large volumes, has varied throughout cosmic history, with starbursts contributing more substantially during earlier epochs when merger rates were higher and when gas fractions in galaxies were larger. The peak of cosmic star formation occurred roughly 10 to 11 billion years ago, when the universe was 2 to 3 billion years old, corresponding to redshifts around 2 to 3. And observations suggest that starburst-like formation rates were more common then than now. Many of the stars in present-day massive galaxies likely formed during these earlier epochs, possibly in starburst phases triggered by the more frequent interactions characterizing the younger, denser universe. The contribution of starbursts to building stellar mass has declined over time as merger rates decreased and as galaxies exhausted gas supplies, making present-day starbursts rarer than their high redshift counterparts. The connection between starbursts and active galactic nuclei, where supermassive black holes in galactic centers accrete gas and produce enormous luminosities, reveals possible coevolution between stellar mass growth and black hole mass growth during major mergers. Many ultra-luminous infrared galaxies show both starburst and active nucleus signatures, suggesting that the same gas inflows, feeding extreme star formation, also deliver material to central black holes. The correlation between black hole mass and host galaxy properties like stellar mass and velocity dispersion hints at connected evolution, where bursts of stellar and black hole growth proceed simultaneously during mergers. Understanding this connection helps explain how supermassive black holes grew to their present masses and how their growth influenced host galaxy evolution through the enormous energy output from active nuclei potentially quenching star formation. The chemical evolution of galaxies proceeds more rapidly during starbursts due to the accelerated formation and death of massive stars that produce heavy elements through fusion and disperse those elements through supernova explosions. The rapid enrichment means that starburst galaxies can build up their heavy element content quickly compared to the billions of years required for steady formation to produce similar enrichment. The enriched material mixes into the interstellar gas and appears in subsequent stellar generations and in any planetary systems forming around those stars. making starbursts important for creating the chemical complexity necessary for rocky planets and potentially for life. The expelled material carries metals into the intergalactic medium, enriching gas that may later accrete onto other galaxies or form new systems, spreading the products of star formation beyond individual galaxies. The use of local starbursts as analogues for high redshift galaxies allows testing of observational techniques and theoretical predictions against systems where detailed multi-wavelength data provide ground truth, building confidence that techniques calibrated on nearby examples work correctly when applied to distant systems. The similarity in star formation rates, and in some cases in gas fractions between local ultraluminous infrared galaxies and typical star-forming galaxies at high redshift, makes the local systems valuable. Templates, despite differences in cosmic environment and in triggering mechanisms. The successful application of locally calibrated relationships to distant galaxies validates the assumption that star formation physics operates similarly across cosmic time, and that local studies provide relevant information about earlier epochs. The remaining mysteries about starbursts, including precisely how feedback operates on small scales, what determines the stellar initial mass function in extreme environments, how superstar clusters form and evolve, and what fraction of gas ultimately converts to stars versus being expelled, drive continuing research and highlight areas where current understanding remains incomplete. The answers to these questions will come from improved observations with next-generation facilities and from more sophisticated theoretical models that capture the complex multi-scale physics linking individual star formation, collective feedback, and galaxy-scale evolution. Each question answered raises new ones, deepening understanding while revealing additional complexity, creating the ongoing cycle of scientific investigation that characterizes mature fields. The perspective gained from starburst studies repositions our view of galaxies from static objects to dynamically evolving systems that experience episodic bursts of activity, punctuating longer quiescent periods, with the bursts leaving permanent marks in stellar populations and chemical compositions that record galaxy histories. The recognition that many galaxies likely experienced at least one starburst phase during their histories makes starbursts central to galaxy evolution, rather than exotic curiosities, demonstrating that understanding typical galaxy evolution requires understanding bursts. The lessons from starbursts inform understanding of normal star formation through the contrast they provide, showing what happens when formation processes that normally operate gently proceed at accelerated rates, revealing feedback and regulation mechanisms that also operate, but more subtly, in normal systems. And as we return to where we began, floating among the young stars of M82, but now equipped with comprehensive understanding of what creates these bursts, what sustains them, and what they teach us, we recognize starburst galaxies as crucial laboratories, revealing galaxy evolution, star formation physics, and feedback processes operating throughout the universe. We return now to the starburst core of M82, floating among the brilliant blue stars and glowing nebulae, where we began our journey. But now carrying the understanding built through exploring triggers, molecular clouds, feedback, life cycles, discoveries, and diverse examples. The young stars surrounding us formed within the last few million years, from molecular clouds compressed by the tidal forces from M81, and they burn with the fierce intensity of massive, short-lived objects that will explode as supernovae long before the sun exhausts even a small fraction of its fuel. The rate at which these stars appear, roughly one every few hours, continues at this moment as new clouds reach the critical density for collapse. New protostars ignite fusion in their cores, and new points of light join the millions already burning in this concentrated region, spanning just a few hundred light years. The process operates according to gravity and thermodynamics and nuclear physics, following laws we understand, even though the environment differs dramatically from the gentle star formation in our local galactic neighborhood. The light filling this region comes primarily from these young stars, their ultraviolet radiation ionizing surrounding hydrogen and creating the pink nebulae, their blue-white visible light dominating when we look at wavelengths our eyes could see, and their absorbed radiation re-radiated by dust, creating the infrared glow that makes M82 one of the brightest infrared sources in the sky. The total energy output exceeds what our entire Milky Way produces, despite M82's smaller size, demonstrating how dramatically star formation rate affects galactic luminosity and how starburst phases represent energetically extreme events in galaxy evolution. The energy flows outward in all directions, some escaping into space, where it travels for millions or billions of years before potentially encountering eyes or instruments that detect it, some absorbed by dust and reprocessed to longer wavelengths, and some deposited into surrounding gas through winds and explosions that will eventually drive the superwind and help quench the burst. The superwind streams, perpendicular to the disk, carrying hot gas thousands of light years above and below the star-forming plane, visible in X-rays as million-degree plasma and in optical emission lines as slightly cooler, ionized material. The wind removes gas that might otherwise form additional stars, creating the feedback loop that ensures bursts remain temporary, even though the physical processes creating them might otherwise consume gas completely before stopping. The outflowing material carries heavy elements synthesized in stars and dispersed by supernovae, enriching M82's halo and potentially contributing to intergalactic gas enrichment, spreading the chemical products of star formation beyond the galaxy that created them. The wind will continue as long as the burst sustains high formation rates, potentially for another few 100 million years, before gas depletion and accumulated feedback reduce formation enough that the wind weakens and eventually ceases. The comparison between M82's few-hour timescale for new star formation and our Milky Way's year or more interval creates the visceral sense of acceleration that defines starbursts, as if galaxy evolution shifted into overdrive and compressed millions of years of normal activity into a 100-million-year sprint. Our galaxy forms stars slowly and steadily, converting molecular clouds at a pace sustainable over tens of billions of years, ensuring gas supplies last through timescales longer than the current age of the universe. M82 burns through available fuel at rates that will exhaust supplies within 1 billion years or less, trading longevity for intensity, creating millions of massive stars in a brief, brilliant phase that fundamentally transforms the galaxy's structure and stellar population. The difference reveals that galaxies live not through steady states, but through phases and transitions, with quiet periods punctuated by bursts when conditions align to trigger rapid transformation. The journey we have taken through Starburst Galaxies began among these blue stars and now completes here after visiting the antennae collision, understanding triggers through tidal compression and gas inflow, exploring the molecular clouds where all stars are born, recognizing feedback as the self-regulating mechanism, tracing life cycles from ignition through peak to decline, learning the discovery history through improving telescopes, touring diverse examples from NGC 253 to ARP 220, and synthesizing scientific lessons about galaxy evolution and star formation physics. Each part of the journey revealed another facet of how starbursts work, building understanding layer by layer through experience and observation rather than through equations or abstract theory. The knowledge emerged from witnessing what these galaxies actually do, from seeing the blue stars and pink nebulae and streaming superwinds, from understanding timescales and rates and processes through their visible effects on gas and light and structure. The other starburst galaxies we visited continue their own transformations at this moment, each one following similar physics, but with unique details reflecting specific circumstances of mass and gas content and interaction geometry. The antennae galaxies remain locked in their slow collision, the cores gradually approaching over millions of years, while star formation proceeds in dozens of superstar clusters throughout the merging system, creating a distributed burst rather than M82's concentrated core event. NGC 253 rotates steadily in Sculptor constellation, its spiral structure still visible despite the intense central starburst, driven by bar-induced gas inflow rather than by external interaction, demonstrating that galaxies can trigger bursts internally through their own dynamics. ARP 220 hides its extraordinary star formation behind thick dust. The merger so advanced that the two original galaxies have lost separate identities, their combined cores creating formation rates hundreds of times higher than M82, despite the dust making visible light observations nearly impossible. The molecular clouds feeding these bursts drift through galactic disks and halos, each cloud a potential stellar nursery, awaiting the compression or instability that triggers collapse into fragments that become individual stars or stellar systems. The clouds remain mostly molecular hydrogen, invisible except through their emission of trace molecules, like carbon monoxide, that serve as proxies for the vast H2 content, existing at temperatures barely above absolute zero until compression heats them enough to begin the gravitational collapse towards star formation. In starbursts, the clouds experience more frequent and more violent compressions from galactic collisions. Tidal forces, supernova shockwaves from previous star formation, and bar-driven turbulence, creating the enhanced formation rates that define the phenomenon. The same clouds exist in normal galaxies, including our own, but collapse more rarely and more gently, producing the lower steady-state formation that characterizes most of cosmic history. The stellar feedback from winds and explosions shapes not just individual starburst galaxies, but contributes to larger-scale enrichment of the intergalactic medium, and helps explain the observed relationship between galaxies and their dark matter halos. The outflows carry metals synthesized during stellar lives and explosive deaths, spreading iron and carbon and oxygen and all the elements heavier than helium throughout the universe, creating the chemical diversity necessary for planet formation and potentially for life. The energy deposited by feedback heats intergalactic gas and creates bubbles and cavities visible in X-ray observations of galaxy clusters, demonstrating that star formation affects regions far larger than the galaxies where it occurs. The self-regulating nature of feedback, where star formation eventually quenches itself by removing or heating the gas supply, helps explain why galaxies don't convert all their gas to stars immediately, and why star formation proceeds episodically through cosmic time. The life cycle pattern of quiescent galaxies experiencing trigger events, undergoing starburst phases, declining as feedback dominates, and returning to quiescence applies not just to individual galaxies, but potentially to most or all galaxies at some point in their histories. Our Milky Way probably experienced starburst phases early in its formation, when gas densities were higher and mergers more common. And the older stellar populations in the galactic bulge might represent fossil starbursts from billions of years ago. The observations of distant high redshift galaxies show that starbursts were more common in the early universe, when galaxies were smaller, gas fractions higher, and interactions more frequent, suggesting the process played a major role in building the stellar populations we see in galaxies today. The current starbursts we observe in relatively nearby galaxies like M82 represent late-time examples of processes that operated far more commonly when the universe was younger. The discovery history that revealed starburst galaxies demonstrates how astronomical understanding advances through technological improvements that open new observational windows on the universe. Early observers catalogued M82 and other peculiar galaxies without understanding their nature, seeing only fuzzy patches different from normal spirals, but unable to resolve detail or determine physical conditions. Radio astronomy in the mid-20th century revealed unusually bright emission, suggesting energetic processes, while infrared observations beginning in the 1980s showed that much of the starburst light emerges at wavelengths invisible to optical telescopes. Each new wavelength and each improvement in resolution added information, gradually assembling the complete picture of rapid star formation hidden behind dust, powered by gas compression, creating blue stars and supernovae, and driving massive outflows. The multi-wavelength approach, combining radio, infrared, optical, ultraviolet, and X-ray observations, became essential for understanding these complex systems. The scientific lessons from studying starbursts extend beyond the galaxies themselves to fundamental questions about how stars form, how gas converts to stars, what regulates formation rates, and how galaxies evolve over cosmic time. The extreme conditions in starbursts allow testing physical models under regimes impossible to study in normal galaxies, revealing whether star formation laws derived from Milky Way observations apply universally or require modification for high-density, high-rate environments. The relationship between gas and star formation, quantified through the Kennicutt-Schmidt law relating gas surface density to star formation rate, shows that starbursts fall on extensions of the same correlation, followed by normal galaxies, suggesting universal physics despite vastly different conditions. The chemical evolution, accelerated by rapid formation and numerous supernovae, demonstrates how galaxies build up heavy element content, and how this enrichment relates to stellar population age and formation. History. The connection between starbursts and galaxy morphology helps explain how galaxies acquire their observed structures, and why elliptical galaxies contain primarily old red stars, while spirals continue forming young blue stars. Many starbursts occur during major mergers that destroy spiral structure and create elliptical remnants, suggesting mergers represent the formation mechanism for ellipticals through processes that include intense starburst phases, consuming most available gas. The post-starburst galaxies, showing red colors from aging stellar populations, but disturbed morphologies from recent mergers, provide evidence for this evolutionary sequence, demonstrating galaxies in transition between spiral and elliptical forms. The observation that massive ellipticals rarely show current star formation, while smaller spirals continue forming stars, supports models where mergers and starbursts represent key transformative events in galaxy evolution. The black holes growing in galaxy centers often show increased activity during starburst phases, with active galactic nuclei and quasars frequently associated with merging systems experiencing rapid star formation. The gas flows funneling material toward galaxy centers to feed starbursts also deliver fuel to central supermassive black holes, creating the observed correlation between starburst and AGN activity and suggesting coevolution of galaxies and their central black holes. The feedback from both star formation and black hole accretion may work together to quench activity, with stellar winds and supernovae joined by AGN-driven outflows in removing or heating gas and ending both formation and accretion. The interplay between these processes remains an active area of research as astronomers work to understand how galaxies and black holes regulate each other's growth. The future observations with James Webb Space Telescope and upcoming extremely large telescopes will reveal starbursts in the very early universe where theoretical models predict they played major roles in galaxy formation and cosmic star formation history. JWST's infrared sensitivity can penetrate dust obscuration and detect distant galaxies too faint for previous telescopes, potentially finding the first starbursts occurring when the universe was only a few 100 million years old. The observations will test whether early galaxies formed stars similarly to modern starbursts, or whether different conditions in the young universe created fundamentally different formation modes. The ability to measure gas and stellar properties in distant starbursts will constrain models of galaxy formation and help determine how the stellar mass in today's galaxies accumulated through cosmic history. The perspective gained from studying these galaxies reminds us that our Milky Way represents one outcome among countless variations. Our gentle, steady star formation, contrasting with the violent, accelerated formation in starbursts, but both following the same physical laws applied under different conditions. The diversity of galaxies reflects the variety of formation histories, environmental influences, and random events that shape each system uniquely, while universal processes of gravity, thermodynamics, and nuclear physics operate everywhere. The starbursts show us galaxy evolution compressed in time, revealing processes that would take billions of years in normal galaxies, operating instead over 100 million year intervals, providing natural laboratories for studying transformation that would otherwise require impossibly long observational programs. The return to M82's core brings full understanding to what initially appeared simply as bright blue stars and glowing gas, as we now recognize the tidal trigger from M81, the compressed molecular clouds, the rapid conversion of gas to stars, the stellar winds and supernovae creating feedback, and the superwind driven by accumulated energy from millions of young stars. The galaxy no longer appears as a static object, but as a system in mid-transformation, caught in a temporary phase between its quieter past and its quieter future, currently experiencing the burst that will shape its structure and stellar population for billions of years afterward. The light surrounding us carries information about all these processes, encoded in wavelengths and intensities and spectral features that astronomers decode to reconstruct physical conditions and formation. Histories. The ongoing nature of the starburst means the process continues regardless of observation, with new stars forming now as we consider the phenomenon. New clouds collapsing, new protostars igniting, new supernovae exploding, and new gas being expelled into the halo. The 12 million light-year distance means the light showing current conditions left M82, when Earth's hominid ancestors were just beginning to walk upright. The burst, already 12 million years old in the galaxy's reference frame, though we see it as present from our delayed perspective. By the time any signal we might send reached M82, 24 million years would have passed in both reference frames, the burst potentially having ended or at least significantly declined, depending on how much gas remained available when we observe it and how feedback developed during the interval between light leaving and our observation of it. The stars surrounding us will have varied fates determined by their masses, with the most massive burning through their fuel in just a few million years and exploding as supernovae. The moderate mass stars like our Sun, lasting billions of years and eventually becoming white dwarfs, and the smallest red dwarfs potentially outlasting the current age of the universe many times over. The massive stars dominating the current light output and determining the starburst appearance will disappear first, fading within 10 million years and leaving behind neutron stars and black holes, while the galaxy's appearance shifts from blue to yellow to red as longer-lived lower-mass stars become the dominant population. The transition from starburst to post-starburst to quiescent galaxy will play out over several 100 million years, creating a fossil record of the burst visible for billions of years in the red stellar population that remains after formation stops. The beauty of starburst galaxies emerges from the intensity and concentration of star formation, creating visual drama through bright blue stellar clusters, pink ionized nebulae, dark dust lanes, and streaming outflows all packed into relatively small regions. The images captured by Hubble and other telescopes show these features in stunning detail, revealing individual star clusters and nebulae and demonstrating that galaxies contain structure at all scales, from individual stars to galaxy-wide patterns. The aesthetic appeal of these images, beyond their scientific value, connects observers emotionally to distant cosmic events and makes abstract astrophysics tangible through visual beauty that anyone can appreciate regardless of technical background. The combination of scientific understanding and visual impact makes starbursts particularly effective subjects for communicating astronomy to broad audiences. The journey through Starburst Galaxies taught us about extreme star formation through direct experience rather than through theory. Visiting M82 and the antennae, and diverse other examples. Understanding triggers and feedback and life cycles through their observable effects. Learning the discovery history through the progression of observations. And synthesizing lessons about galaxy evolution and formation physics. The knowledge built gradually through accumulated observations and careful interpretation, each fact supporting others in constructing coherent understanding of complex phenomena operating across vast scales of space and time. The starbursts revealed themselves through patient observation using multiple wavelengths and techniques, demonstrating how science progresses through careful measurement and logical inference from data. The ending of this exploration comes naturally after having experienced the phenomena directly, understood the mechanisms thoroughly, and placed starbursts in their broader cosmic context. The starbursts continue throughout the universe, in M82 and in thousands of other galaxies near and far, each following the same general pattern, while displaying unique details reflecting specific circumstances. The process will continue as long as galaxies contain gas and experience interactions or other triggers, ensuring starbursts remain part of galaxy evolution for the remaining lifetime of the universe. The stars formed during these bursts will persist for billions of years afterward, carrying the legacy of their intense formation in their chemical compositions and spatial distributions, preserving the memory of the burst long after it ends. We leave M82's star-forming core with understanding that transforms observation into comprehension, seeing not just blue stars and pink nebulae, but recognizing the physical processes creating the appearance, the tidal trigger beginning the sequence, the molecular clouds supplying the raw material, the stellar feedback regulating the process, and the temporary nature of the intense phase we currently observe. The light from these stars will continue traveling outward through space, potentially reaching observers billions of years and billions of light years away, who will see M82 as it appears now, preserving this moment of galactic transformation for the distant future. The journey ends here among the brilliant stars where it began, completing a circle that took us through experience, understanding, examples, and synthesis, returning with knowledge built through careful observation and patient explanation of one of the universe's most energetic and beautiful phenomena, where stars are born every few hours and galaxies transform through intensity and violence into structures that will persist for cosmic ages, beneath skies filled with young blue light. In regions of space where creation proceeds at extraordinary rates, following natural laws that operate throughout the cosmos, creating beauty through physics, wonder through understanding, and connection through light that bridges the distance between these distant stellar nurseries and our quiet moment of observation here and now, as the starbursts continue and the universe goes on creating stars.